Hello physics people, good morning. I wanted to go through some of the aspects on chapter 9 since I had missed the Wednesday before spring break when you guys took the quiz. We didn't get to cover this as much as I would have liked to. Some of the concepts in here are probably new and may require a little more time to discuss, so I just wanted to make a few videos to kind of supplement our class time. I'm going to do the same for logic, by the way, since yesterday's logic discussion was such a fail. But anyway, let's go through physics. So as always, these are the primary objectives and things that you need to know for your test. So what I'd like to do is just kind of walk you through these this morning, which, by the way, these will all tie into what is also back here on your study questions. So we're just going to pretty much talk through all of these and make sure we hit these key points. It'll probably take a couple of videos. So I might do it in pieces, and then when I get that done, then I'm going to finish going through these problems and the exercises, and then these if they're not something that we didn't already discuss. All right, let's get started. So first thing to understand, again, is I would recommend that you have on your flashcards a lot of these key things that we're going to go through right here, because these are the things that will show up on your quizzes and your test. So I'm going to set this to the side so I can talk. First thing on the list, of course, is to explain what a wave is. Now we've gone through this a couple of times, but I'll do it again really quickly because it's important to understand these terms. So what is a wave? First thing to understand, a wave is not a substance in itself. So for example, a wave is not this slinky. Okay, the slinky is made of matter, but the slinky is not a wave. However, I can make a wave on the slinky, right? And what is the wave? The wave is disturbance of my matter. So the wave is not matter itself, it's a disturbance of existing matter, in this case, my slinky. So a wave is disturbance, not matter. That's a key thing to remember. And you have to ask yourself, what is being disturbed? But let's talk first of all about the shape of a wave. So we've gone through this a couple of times. There's two ways to look at a wave. You can look at it in terms of distance, which I'm going to put meters here. Okay, so I can have a wave that looks like this. I can draw a little better here than I can on the whiteboard at class. Okay, so this isn't perfect, but you get the idea. This is an example of a wave. Let me go ahead and bring it. Okay, so what are the important parameters to understand about this wave when we're thinking of it in terms of distance? In other words, this is the disturbance. We're looking at it with length. Well, there's two things. First thing is to remember that this distance from here to here is what is called the amplitude. And this distance from, I'll do it down up here, from here to here, one full cycle, is known as the wavelength, which they call lambda, wavelength. Okay. Now these are called peaks. So anytime you're at a top, that's a peak, and this is called a trough. So we have a peak and a trough. Okay. You could also call this a crest. I guess that's what he calls it in the book. So a crest or a peak and a trough. So wavelength and amplitude. These are the important things to remember here. Now, what is the equation? They talk about this a little later in the chapter, but there's an equation that we're given that relates wavelength. We'll get there later. Okay, so what if I want to look at the wave with respect to time? Let's do that. As it changes with respect to time. Okay. I'm kind of coming off my board there. Okay, so now I'm looking at this with respect to time. Let me push this up a little bit to get away from the reflection. All right, so now what I'm looking at is between the peak and the trough, how much time is there from one complete cycle, from one peak to my trough back to the peak again. One complete cycle, this is called a period. Okay? Now I still have amplitude here. This is still amplitude, which remember is half the full distance. But in this case, I'm looking at time. So period is how much time from one peak to another. Now we can also talk about this in terms of frequency. So frequency would be how many peaks or troughs pass a particular point in time. So how many of a complete cycle will pass this point in time, and that would be called a frequency. Let's see, what else do they want us to understand? Let's come back to the book. So they want us to be able to explain graphically crest, trough, amplitude, wavelength, and period. Okay, so we just did number 1 and number 2. Check, check. And we were talking about frequency and frequency of a wave and period. So frequency, again, usually little f, is how many, there we go, how many cycles per second, how many waves per second pass a certain point in time. So frequency, as we talked about yesterday, frequency is usually defined in hertz, which is the same as 1 per second. Or you could call it a cycle per second, but as we said, cycle is usually unitless. So usually it's just sort of 1 per second, which is also known as a hertz. So how many cycles per second, how many wave cycles per second are passing a particular point in time? That is the frequency of a wave. Okay, the next thing they want us to talk about here, and we have talked about this, but it has been a couple of weeks, they want us to go through the 5 types of wave interactions. So let's go through and talk about each of these. Okay, so there are 5 types of wave interactions. We have reflection, refraction, diffraction, resonance, and interference. Okay, let's take these one at a time. First, okay, we're going to talk about the different kinds of interactions here. So, reflection. What happens with reflection? I'm going to use the example of a light ray like they use in the book. So when we have a light ray that's coming in and approaching a reflective surface, a mirror or some kind of shiny surface, it's coming in at a particular angle. Here's the vertical line. It's coming in at a particular angle we'll call the angle of incidence. Now the law of reflection states that the beam is going to reflect out at the exact same angle at which it came in. So this is reflection. I use the example of a light ray, but the same would apply to sound. Let's suppose you're standing on the edge here of a large canyon and you holler out, hello, 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 hello. Your sound wave is going to come out and it's going to hit the opposite end of the canyon. And what's going to happen there is it's going to hit and then it's going to reflect back at you. Actually, I guess I should go at this angle, right? So it's reflecting back at an angle of incidence the same as when it came in, but of course it spreads out, so you hear the reflection on the opposite side. It sounds fainter because as it's spreading out you're getting less amplitude, but that's an example of reflection of a sound wave. Now you could also see reflection of a water wave. Let's say you're in your bathtub and here's the faucet that's dripping water into your bathtub. So as it drops water into the bathtub, you see the spreading ripples like this. Okay, it spreads and spreads until it gets all the way over here to the opposite side. There's an example of reflection right there, by the way. So what happens when, try to get away from my reflection from my light, what happens when the wave gets all the way over here? It hits this surface and it's going to reflect back. So then you're going to see waves reflecting back off the back side. So we see reflection of waves happen all the time. Let's talk now about the second type of interaction, which would be, so we talked about reflection, now let's talk about refraction. Refraction is basically when a beam is bent. So let's talk about it first in the sense of a light ray. I'm going to use a prism because I think that's the coolest example. So I have a light ray that's approaching it. Now I'm drawing this light ray as solid, but in actuality we know that white light is actually a combination of all the light together. So you would have a red superimposed over all the other colors all the way down to purple. And in a second we're going to talk about interference and why they all add up to be white. But so I'm just representing this light ray as a beam. So imagine this is I've put it through a slit or something like that to get a very concentrated ray of white light. So it hits this surface. Now here I have air, but here I have glass. The speed of light changes when at this surface, when it goes from one medium to another medium. It's actually bent a little bit. So what happens is it's actually going to bend, I forget if it's going to bend down or bend up. It's actually going to bend down just a little bit. So normally I'll just draw it like this. The ray would bend down a little bit like this because it has been refracted or bent. And then once it reaches this other surface over here, it's going to bend again. So in actuality, what happens with the light ray is we have the different individual rays that are coming in. Remember, this is really a composite of multiple rays. So your red light is coming in, and it's going to be bent a little bit, and then it's going to be bent again when it gets here. On the other hand, the purple is coming in, and it's bent to a different degree, and when it hits this surface again, it's bent. But what we end up having, the net result, is this composite light ray with all these different rays inside it are bent to a different degree, and therefore we have the spreading over here that gives you your rainbow effect. But the key thing is refraction is the bending that occurs when a wave travels from one medium to another, and so at that surface is bent. The velocity changes, and so it bends the ray. So that's refraction. Okay, so let's talk about diffraction. Diffraction is kind of interesting. So let's say I have this sheet here with a slit in it, and the easiest example, honestly, is to look at water. We did one of the simulations of this in class. So let's suppose I drip water in here, and so I have these spreading ripples. They actually are all the way around. I have these spreading ripples that come and then they hit right here. What's going to happen? Well, some of this is going to reflect back that way, but what happens as it goes through this tiny slit? Some of the ray is going to transfer through. You actually see a little bit of bending around the corner, so what you end up having is something like this. Now, if you think of it in terms of a light ray, let's suppose I'm shining a light ray at this surface. The light actually, as it's passing through, bends a little bit around this, so it actually spreads out some. So you may have a tight ray coming in, but what you see over here on the opposite wall ends up being kind of a fuzzy, has fuzzy edges, because some of the light comes straight through, but some of it is bent a little bit, coming more out like this. So you've probably seen this before. Sometimes you'll see a shadow that seems to be very indistinct, a little bit fuzzy on the edges, and that's why, because diffraction is a phenomena when a ray actually sort of bends around a surface or around a corner a little bit. A good example also they frequently talked about is if you have a light ray and then you put in front of a tiny little, let's say, a piece of lead. So this is a laser, say, and I'm going to put a tiny little surface in front of it that is a piece of lead. Whoa, just went out of focus there. Now what you would normally think is, well, the light is going to hit that and it's going to stop, but it actually doesn't. It actually sort of bends around it a little bit. So again, what you see on the opposite side over here is it's not perfectly square. Again, it's going to be kind of fuzzy on the edges. So you see a surface like that. And it actually will have breaks in it, which we're about to talk about why that would happen. That comes into when you talk about interference. But diffraction basically is when a ray, a wave, bends around a corner. So you would see the same here. If I've got a ray coming this way, it's going to kind of bend around this corner, and so I get some bending there. So that is diffraction. They talk about it a little bit in the book. Let's see, I think there's an illustration in the book here as well about diffraction. Yeah, here you can't see it very well, but this is the example where they're using two rays that are coming through a tiny slit. And notice, if you can look at it in the book, you'll notice what happens here is sort of a range of dots. You can see it better if you look at it in your book, and they explain a little more. So what they have there is they have a ray coming, the sheet looks like this. It has several slits in it, and they're shining the light at that, and what you see coming through, there's slits along here, is you see the light bending at each of these places like this. Let me draw that bigger. That's probably kind of hard to see, isn't it? So you have this sheet that has slits along here, okay? So these are slits. So what happens as I'm shining light this way is the light ray, some of it goes straight through and some of it kind of bends a little bit. So I have a little bit of a spreading at each of these slits here. Now when you take the spreading of the light and you continue it all the way out here, you'll see there are some places here where they overlap, so the light from this one and the light from that one are adding together, so it's going to be brighter right here. So right here I'm going to have a brighter spot, and likewise right here, because I have overlaps, I'll have a brighter spot here. Normally you would think, well, light is traveling a straight line, it's just going to go through the slit and I'll have a very distinct dot right here. But it's not. The fact that it spreads out and you have a big circle over here illustrates the fact that it's being bent at each of these edges, and that's called diffraction. Alright, so now let's talk a little bit about resonance. Resonance is our next one we're going to talk about. So every system, every mechanical system has a desire to vibrate at something we call its natural frequency. The natural frequency of a system depends on its geometry and its mass. So let's say, for example, you have a toy that has a spring, we'll say, coming up like this, and on top you have a mass. So in one case you have just a big ping pong ball, so it's kind of lightweight. But now let's suppose you have the same toy with a spring, and on top of it I put a solid steel ball or something like that. Okay, this is a ping pong ball. I'll just call it ping for short. If I take this ping pong ball and pull it back this way and release it, you know it's going to vibrate back and forth. But you can also imagine in your mind it's not going to vibrate a whole lot. Now what would happen on the other hand if I pulled this steel ball back the same amount and released it? Because you have this mass at the top of the spring, you know what's going to happen. You know that it's going to vibrate much more dramatically. Why is that the case? If the geometry of both of them are exactly the same, why would this one tend to vibrate more? Well, it has to do with the greater mass here. Now, likewise, you know that if I have a toy with a short spring and a ball, it's going to vibrate back and forth less than if I have one on top of a long spring. Okay, so just intuitively by playing with things, you know that even if I disturb each of these by the same amount, they're not going to behave the same. They're going to vibrate differently. It's because each of them has a place we call natural frequency, which is based on its geometry, where it would tend to want to vibrate. And again, that natural frequency is a function of the geometry of a system. Now, what happens if, let's say we have a building, a very tall building. And here you are up here in the window. That's a very big face for a very big building. Alright, so this building is similar to the example I was drawing of a mass on top of a spring. If I were to try to disturb this building somehow, it would vibrate. Hopefully not much, but it would have some vibration. So for example, in an earthquake, if the ground is vibrating, it's going to cause this building to vibrate also. And the natural frequency of this building is going to depend again on its geometry, its mass, all of those kinds of things. Because depending on how a building is built, it's going to tend to damp, in other words, reduce those vibrations, absorb them. But what happens if we have an earthquake that comes along, and it just so happens that the earthquake, the frequency that this earthquake is vibrating this building exactly equals the natural frequency of this building. What will happen is this energy happens to hit what I could call the weak point of this building, and it becomes much more energetic, so it's going to dampen that vibration less, causing this building to vibrate even more. So resonance is an example of when you are sending a forcing function into a system at its natural frequency. So coming back to my ball on the end of a spring, okay, this has a particular natural frequency. If I were to pull it back and then release it, I know that it's going to vibrate back and forth. It's going to kind of vibrate back and forth here at its natural frequency, eventually damping out and stopping. But what if I put a fan over here that's blowing constantly at this, and it just so happens that I'm blowing at this at a velocity that equals the velocity with which it's going back and forth. So I just happen to add to its natural frequency. The system can't really dampen it at the natural frequency, so all of the energy from this is going to be it's going to be undamped, and so the vibrations here are going to become much more dramatic, and that's what we would call resonance. When I'm sending a vibration into it that exactly equals the natural frequency. And this can happen in a couple of ways. I can put a forcing function outside, like in this case a fan that's blowing on it, or I can be pulling this back and forth or pushing at it at exactly its natural frequency. Sorry, I got interrupted there. Alright, so back to talking about resonance. Let's talk about it in the case of a bridge. This is something that I think we talked about in class. So I have a suspension bridge between two pylons. This suspension bridge is going to have a natural frequency that's going to depend upon the distance between the two supports, the geometry of the bridge itself, how rigid it is, all kinds of different things. If I were strong enough, if I were Superman and I could come pull this bridge this way and let it go, it would swing back and forth at its natural frequency. Now again, what if I have wind that's blowing across this at just the right velocity of wind? It could excite the natural frequency of this bridge, add to it, and cause the bridge to vibrate at more than it would normally do because it's not able to dampen that frequency. So resonance is when you end up with greatly exaggerated amplitude because the forcing that I'm putting on it just is adding to the natural frequency. Now I can do that. In the book they talk about it in terms of reflection. So instead of it being an outside force coming back, it can also be reflection. So let's use the example of a well, let's see if I can do my slinky. Not sure I can illustrate this very well. I'm not going to be able to illustrate resonance on here. But when I vibrate this back and forth, of course, you see Saw the reflection coming back there, right? It hit the surface and bounced back. Now what if, as I'm vibrating and the reflection is coming back, what if the two of those just happen to equal the natural frequency? And they add together, they're going to continue to add together, and I'm going to have an exaggerated amplitude. In the case of music, that's what we're referred to as harmonics, and he talks about that quite a bit. All right, let's talk about interference.